Hi, my name is Mel, and I do videos sort of in a presentation format. One, because I have autism, and two, because it's just what suits me. Doesn't suit you, oh well, sorry. So I'm going to introduce concepts and fundamentals of abiogenesis, alright? So we'll cover sort of like, so the origin of life from non-living matter. So cover historical background, key theories, experimental research, and what some implications might be. So I'm going to cover the definition and history of abiogenesis, prebiotic, which is pre-life Earth conditions, chemical building blocks, key experiments, theories, formation of protocells, transition to biology, current challenges, modern research tools, and some future directions. So the following section includes the concept of abiogenesis, its historical context, how it differs from biogenesis, and while understanding abiogenesis is crucial for unraveling life's origins. So abiogenesis refers to the natural process by which life arises from non-living chemical compounds. Historically, ideas have evolved from spontaneous generation to the more rigorous scientific hypotheses that were developed during the 19th, 20th, and 21st century. Okay, and I just want to say, like, there's no lack of the ways that abiogenesis could have occurred. There's many different paths that could have happened. And that's half the issue because we can show how many different patterns and how many different paths of how this could have occurred, right? So are we going to know for 100% sure how it occurred? Probably not, but we know that it did, and it was entirely possible for it to happen naturally. So biogenesis, that is the concept that life only arises from existing life, while abiogenesis explores how life initially emerged from non-living matter, highlighting a fundamental distinction in biology and origin of life studies. So we're talking about chemical elements. There are 118 chemical elements in the element table. So we're talking like there are different elements obviously will bond chemically with other elements, and we're talking about then going to like to molecules, and some, like carbon is obviously the basis of all life on Earth. Carbon's one, phosphorus, there's others, So we're just looking at basic like chemistry, and then we're talking about biochemistry. And for people to say that abiogenesis can't have occurred, they're saying basically that molecules can't form, which is ridiculous because obviously they can. So studying abiogenesis helps us understand life's beginnings, informs astrobiology, guides synthetic biology, and addresses fundamental questions about existence and life in general. The following section explores the probable environmental and chemical characteristics of early Earth that provided the setting for life's emergence. So early Earth was different than what we have now, okay? It's just not the same. It was a dynamic planet with volcanic activity, oceans, eventually, after a few million years, harsh atmosphere, creating conditions conducive to complex chemical reactions necessary for life's origin. So there's different, like Earth was also had like a bombardment of meteors and stuff like that, like very early on. So like some of the water that came from on Earth came from that, and some of the other elements necessary for life also came on that. So we are not talking about rocks formed life. We are talking the elements bonded to create molecules, which eventually formed RNA, DNA, and lipids, which would form a cell. All right, so you'll hear some creationists talk about, how we think, people came from rocks. It's not what we're saying, okay? We're talking the chemical elements that were in on the earth and in the rocks, okay? Yes, big difference. The early atmosphere was reducing or neutral, containing gases like methane, ammonia, and hydrogen, which is energized by lightning, UV radiation, and geothermal heat. That was critical for prebiotic chemistry. And we had a lot of wet-dry cycles as well, okay, which would have helped with this sort of stuff as well. Geological features such as hydrothermal vents and mineral-rich environments, or shallow, very shallow pools, as I said, wet-dry cycles is often what's touted these days, provided catalyst and energy that facilitated molecular synthesis and organization. The following section covers the formation of the essential molecules that form the basis of life. So we're talking DNA, RNA here. Simple organic molecules, including formaldehyde and hydrogen cyanide, formed under prebiotic conditions, serving as precursors to more complex biomolecules. Okay, so we're talking sort of prebiotic. Amino acids are nucleotides fundamental to proteins and nucleic acids, were synthesized through natural processes and are central to life's chemistry. So you might hear adenine, cytosine, thymine, thyrosine. And there's uracil, which is in RNA. But like they are amino acids. You can see it's sometimes represented as letters. But you've got to understand that each of these amino acids are chemical molecules in their own right. All right? And nucleotides are also chemical molecules in their own right. Right? As are proteins and nucleic acids and all that sort of stuff. All right? Water acted as a solvent facilitating reactions, while minerals served as catalysts and surfaces aiding molecular assembly and stability. The following section highlights pivotal experiments that have shaped the understanding of life's origins. The Miller-Urey experiment is a common one cited, demonstrated that organic molecules could be synthesized from simple gases under simulated early Earth conditions. It was a landmark in origin of life researches, and much more research has occurred since then. And it's the research in origin of life in terms of abiogenesis is progressing really quickly. So just saying, this is sort of like the origin sort of thing that they did. Following Miller-Urey, numerous studies expanded knowledge on prebiotic synthesis, including experimentation on nucleotide formation and polymerization. Okay, that's polymerization is how simple molecules could polymerize to form complex biological molecules. Okay. Contemporary research uses advanced technology to simulate diverse environments and explore complex pathways to life, which include like wet-dry cycle, hydrothermal vents, and RNA synthesis. The following section reviews major hypotheses explaining how life originated from non-living matter. There is one that everyone's probably heard, the primordial soup, which has sort of gone out a little bit out of fashion, but that proposes life began in a nutrient-rich soup of organic molecules energized by environmental resources, leading to increased complexity. Sort of, they've modified a lot of these theories now, so there's different theories as well as this one, and they've modified this enormously. So you'll hear this primordial soup cited by creationists, but it's not. This is sort of like an older paradigm. They still think that life began in, sort of like wet, dry water cycles, but yeah. The hydrothermal vent hypothesis suggests that life originated around deep sea thermal vents, where mineral-rich warm water provided energy and catalytic surfaces for molecular assembly. RNA world hypothesis posits this that RNA molecules were the first self-replicating systems capable of storing information and catalyzing reactions, bridging chemistry and biology. And there's a fair bit of fair bit of evidence that this may have been. But as I said, look, there's so many different ways that abiogenesis could have happened. So the following section explores how simple molecular assemblies evolved into cell-like structures capable of maintaining an internal environment. Lipids form naturally to form bilayers and create membrane boundaries essential for separating chemical environments and forming protocells. All right. These structures are early models of protocells formed by spontaneous aggregation of molecules, demonstrating compartmentalization and primitive metabolic activity. And probably what happened is that DNA or RNA floated into a lipid bilayer cell, and a very, very primitive protocell was formed, and this would have replicated itself, by different means. Encapsulation of RNA or similar molecules within protocells allowed for protection and replication, critical steps towards living cells. So in that encapsulation, yes. So you can have RNA encapsulation or DNA encapsulation and other ways as well. The following section outlines how purely chemical systems evolved key biological functions such as metabolism, reproduction, and evolution. Primitive chemical pathways emerged that enabled energy transformation and molecular synthesis, foundation to living systems. Molecular self-replication and inheritance mechanisms developed, allowing information transfer and continuity of life forms. Selective pressures favoured increasingly efficient and stable molecular systems, driving evolution from chemistry to biochemistry to biology. So you can have molecular evolution, right, as well here. The following section discovers the current limitations, debates, and mysteries that might remain in abiogenesis research. Many models rely on assumptions or incomplete data, and a comprehensive explanation of life's origin, while they're there, they need to be sort of better spelled out. And like I said, there may not be just one way it happened. So it's not so much elusive as there's too many options. And not all models have incomplete data. There is incomplete data. Like we have many of the steps in many of the models. There are some missing steps, but this sort of I just want to say we do have a lot of information about abiogenesis. So, but there is more research to be done. Clearly, Scientists differ on plausibility of certain hypotheses. Well, there's a lot of debate in abiogenesis and a lot of papers and research being done. So this is not no one's assuming anything, right? So they are testing different ways and different means to see what happens, and all sorts of different things are coming up. They often do computer simulation and real world simulation, and the interpretation of experimental results and underscoring the complexity of the subject. And you're going to think, however many million years that this took to occur, we've only been exploring this for not that very long. And as I said, science is progressing, and we have a lot of the steps in the process. We do not have all of the steps, okay? Questions remain about the exact pathways, some of the environment conditions, and molecular mechanisms that might have led to life emergence. So look, obviously as I said, we do have answers to a lot of this, but as I said, more research to be done. We know it's possible and plausible. There's no evidence at all that anyone came and waved a magic wand and occurred, the first life to form, right? There's absolutely no evidence, and it's not necessary. The following section highlights the advanced methods enabling deeper exploration of life's origins. Techniques such as mass spectrometry and spectroscopy allow detailed analysis of complex chemical mixtures and reaction products, among other things, all right? They're just among some of them, right? Computer simulations and molecular modeling help predict reaction pathways and environmental interactions relevant to abiogenesis. Collaboration across chemistry, biology, geology, and computational science is critical for understanding of abiogenesis. And you might also say astrobiology, physics, others as well, that would all have to come into this, right? The final section discusses how abiogenesis research impacts other fields and outlines potential future research pathways. Understanding abiogenesis aids in search for life beyond Earth, guiding exploration of other planets and moons. So astrobiology and extraterrestrial life, if it exists. And look, I don't know when it comes to if there's any life on anywhere else other than Earth. I'm not well up on enough on the subject to really know. I think it's likely that life of some form probably exists elsewhere in the universe. Whether that life's intelligent or not, I think that's a low chance, but I think it is possible. Whether we'll meet them in life, I think that's a very low possibility. But I do think that it's very possible and plausible for some sort of life to exist elsewhere. And look, I don't think we're still discovering stuff all the time. And I think it's very possible, even if it's very low possibility, of intelligent life of some form occurring elsewhere. Okay. But the thing is, that's not something, I think the more we know about abiogenesis, chemistry, physics, astrobiology, astronomy, and all that sort of stuff, the more we know about it, the more we might be able to sort of understand if life could exist elsewhere. And look, it could be, and it's likely, that life of some form is rare. All right? It could be that life existing is rare. Doesn't mean it's impossible to exist elsewhere. I mean, the universe is a very, very big place. It could even be, however unlikely, that life exists elsewhere in the Milky Way galaxy. But space is really, really big. And while we know some things we can look for, I don't think we know everything we should look for in terms of life. And look, as I said, I think the universe there's trillions of stars and planets and galaxies. I think obviously I do think it's very possible life exists as well, but obviously don't know that. So, insights from abiogenesis inform the design of artificial cells and novel biological systems with practical applications. And artificial cells are a big thing too, and also too, using CRISPR to alter people's, with genetic diseases, alter DNA to help, cure genetic illnesses and stuff like that. The more we understand about abiogenesis, biology, chemistry, and all that sort of stuff, the better off we are to help ourselves, help the planet, and understand things. I mean, research is happening very rapidly. And this is what I'm saying is, no one is assuming everything. They research this. There's a lot of there's a lot of scientific papers, right? This is not, no one's turning around and going, oh yeah. So the study of life's origin raises important questions about the definition of life, humanity's place in the universe, and ethical implications of creating life. And look, a lot of people now view viruses as some form of life. They don't self-replicate, but most people do think that viruses are a form of life because they definitely have, they do mutate and they do evolve, they do change. So obviously, what do we consider life is going to be something we're going to have to start really thinking about. Obviously, too, about humanity's place on the world. I mean, humans are a form of life. We are related to every other form of life. We are evolving beings. Evolution is a thing. And our place in the world, I mean, we are reliant on all the other biological and ecological systems on the world. And we're plundering the world for all its resources without a care in the world. And we're basically seeding our own destruction. So I think understanding the fact that we are so dependent on the earth and so dependent on what biological and chemical resources, I think helps us understand to care for the planet. And also too, if in a couple of 100 years humans start spreading to other planets and eventually to other stars, which we will have to do if we want to survive when our sun burns out, which is about 1 billion years or so, or expands to where we can't survive anyway, then obviously this is something I'm not sure even if that's something we should want. But we also, the ethical implications of creating life, even if it's artificial life or artificial intelligence that can mimic life, we should understand that, I think. That's important. So look, abiogenesis research combines many disciplines to unravel how life emerged from non-living matter. Despite challenges, ongoing studies continue to advance our understanding with profound scientific and philosophical implications. And I don't think it's fair to turn around and to throw your hands up and say some sort of God did it. I think that's not an answer because you don't know how God did it or why God did it or even if a God exists. And look, if people want to believe in some sort of God, good for you, but your belief in God should have nothing to do with science, all right? Okay, so that's me for today. Thank you.